All right, so this is the chapter about the origins of quantum mechanics, talking about the early difficulties in explaining the experimental observations and also the motivations, the strugglings of those pioneers. Okay, you're going to see some stories. Okay, so a lot of these materials actually are based on the book by Malcolm Langell, Quantum Concepts in Physics. Okay, so this is a very good book for you to understand the origin of quantum mechanics. Actually, it's famous that Albert Michelson made a statement in 1903 saying, "Our future discoveries must be looked for in the 6 places of decimals." So many people actually have some kind of misunderstanding of this statement, thinking that Michelson was mentioning that the physics was almost complete. So what's left are only details. But actually, we believe that he and the physicists of his age believe the opposite. Okay, we know that the devils are always in the details. Okay, so the measurement in the 6th place of decimals, that means a more precise measurement. We know that the precise measurement always need to surprise new discoveries and new frontiers. Okay, so there is a statement by Maxwell a little bit earlier that gives us a better picture of this statement. And Maxwell said, "I might bring forward instances gathered from various branches of science showing how the labor of careful measurement has been rewarded by the discovery of new fields of research and by the development of the new scientific ideas." As a note, Maxwell is not only a very good theorist, he's also a very good experimentalist. Okay? And this statement by Maxwell actually is exactly how quantum mechanics, how the development of quantum mechanics benefited from the measurements, from the wonderful adventures by the experimentalists. Okay, and to quote this one, actually I want to cite a kind of a funny statement by Donald Rumsfeld, then the Secretary of Defense of the United States in 2002. Okay, he was remarking on no evidence of Iraq having a weapon of massive destruction, okay, which was critical, to whether or not the U.S. and the allied armies should attack the Iraq, okay, using the United Nations as a backup. Okay, and his statement actually is very interesting. Let me read this one word by word. Okay. Reports said that something hasn't happened are always interesting to me, because, as we know, there are no knowns. There are things we know, and we also know there are no unknowns. That is to say, we know there are some things we do not know, but there are also no unknowns. The ones we don't know, we don't know. And the unknowns actually are the most important, the most revolutionary discoveries that a scientist could have dreamed of. Okay? And this one could only be made by measurement on the extreme conditions, such as very small scale or very large scale, very low temperature or very high temperature, very high pressure or very high vacuum. On all these extreme conditions, the measurement at the 6 places, allow this in the 18th places of decimals, actually can bring us surprise that we could never expect. We don't know that we don't know. Okay. For example, if you look at I don't know how many of you know about this news about the gravitation waves, right? Recently, there's a report about the gravitation waves detection of the black holes of of mass about 85, solar mass, combined into 140 solar mass black holes. And this actually is a big surprise to the black hole theory. Okay, and this one could be known only by experimental, by the measurements. Okay, if there's no such precise measurement, people would have no chance actually to even see such kind of phenomenon. So the unknown nodes actually are the real frontiers of scientific research. Okay, and in the 19th century and early 20th century, there are a lot of surprises. Like there are a lot of unknowns that become known by this precise measurement. So we're going to see how the development of the devices of the instrument have enabled the new discoveries, which in turn lead to, and force the scientists to accept those difficult and profound new concepts in physics. So this is the structure. I try to group this one. So in the beginning, people already know something about atoms by chemistry, and there's the knowledge, there's already establishment of the statistical mechanics by Closius, Maxwell, Boltzmann, Gibbs, Einstein, so on and so forth. Okay, and there's also a very beautiful and complete theory of light by Maxwell, and verified by the experiment by PHYS. Okay, so this was the foundation. And then from that on, people understand the structures of the nucleus, atoms, okay? And the atom spectrum, black body radiation, and also, the wavelength of the EM waves, of the light, right? And then people try to build models to understand the atoms, and that comes the Bohr's theory. And also there's Einstein's theory about the optical transitions, the emission and the absorption of atoms, okay, and also the correspondence principle by Bohr. And then Einstein introduced this photon concepts of photons. So that's the kind of another stage of this quantum theory, called this old quantum theory. And then there were two geniuses, okay, based on the difficulties and the developments before them, especially by Bohr, by Einstein, okay, and De Broglie and Heisenberg, okay, so they, went through two routes and to provide the most original ideas. One is based on the matter wave. Another one is based on this kind of only observables should be in the theory, which must be between two states, must be a transition. Okay, so that introduced the matrix, which leads to the quantum mechanics. And then De Broglie's matter wave leads to the establishment of the Schrodinger's theory of the wave dynamics of quantum mechanics, and then that leads to the unification. Okay, and then the quantum mechanics again combined with relativity leads to the Dirac equations and quantum field theory. So all of this one actually can be grouped together, called the first quantum revolution. Okay, and this actually is very musical. It's very exciting. It's like a beautiful summary of duality, a duality of matter and light, a duality of particle and wave, a duality of matter and information. Okay, so I can put this one at the background, the music notes. So you can see that we can see a lot of strong notes in this symphony. Okay, and so you have heard this music. So I don't want to replay this one. So this is a symphony, the fifth symphony by Beethoven. It's also a beautiful integration of duality. Okay. So we can take a break. let's start this introduction. So the movement one of this symphony starts with the cross. Okay? In 1900, Sir Kevin stated that the beauty and the clearness of the dynamic theory, which asserts heat and light to be the modes of motion, is at present obscured by the two clauses. Okay, so these two clauses are famous actually. So I don't need to hide. So they are black body radiation and make some Morris experiment of no ether, right? So this is the two clauses by the time of 1900. Okay. So let's start with this chemistry, the discovery of atoms by chemistry. We know that the atoms in the ancient days actually have been proposed by, for example, Plato and other philosophers as the elements for building this universe. Okay, but really, the modern concepts of atoms started with this chemists using, thermodynamic laws to prove the matters are indeed made of some elements and made of some indivisible, chemically indivisible particles, and they call them atoms. So actually, before Dalton, people already know that there is a conservation of mass in chemical reactions. That means you can put 1 kg of oxygen and some mass of hydrogen and put it together the reactor and get some water. But if you measure the mass before and after, they're always the same. Okay, right? And then John Dalton, and they try to measure the reaction of the gases, and they use this device called a eudiometer. Okay, so they can collect the gases, the reactant gases, okay, and the products, and then to measure the pressure, the volume, and the temperature of this gas before and after the reaction. And he found an interesting relation. That is, you can measure the pressure of each individual gas, or you can mix them together. You find that at the same temperature, okay, keep the volume at the same. You find that the pressure actually has a very simple multiple proportion, summarized as P equals PA plus PB and PC and so on and so forth. So that means they're just a simple addition of the portions. Okay, and then of course, and then this was applied to the reactions, chemical reactions, and they found that the volumes, for example, of different gases before and after the reactions, they actually satisfy some very interesting rational numbers represented proportions. Right? For example, if you use 2 volume of hydrogen and 1 volume of oxygen, that will produce just 1 volume of oxygen. Right? You can put 1 volume of oxygen and 1 volume of carbon monoxide. Okay, sorry, 2 volume of carbon monoxide, and then you can produce, actually 2 volume of carbon dioxide, right? For example, so on and so forth. So this one actually, give us a very strong evidence of, the portions, okay? So the concepts of the molecules and the concepts of the atoms. So that means you can actually have this imagine that all these gases are made of kind of elements, and these elements they have to be combined, at a certain portion. Okay, and then Avogadro, of course, interpret this M as the number of molecules. Okay, so eventually this leads to the concept, the modern concept of atoms. For example, this is the atom model by Dalton, and he imagined that all the atoms are solid, compressible balls. Okay, and they can combine because of their some properties. They can combine to each other according to some properties, some inner structures. Okay, and so then you can mix them, you can change them the composition, but you can never divide these atoms. So the atom means actually indivisible. So I would say this is chemically indivisible. Okay, so that means in all the chemical reactions, the atoms are the smallest units that can participate. So this is the first development of the concepts of atoms, which turns out to be very important later in quantum mechanics. For a lot of quantum theories actually have been trying to understand the structures of atoms. And then, of course, Mendeleev and Mayer, they independently classified all different elements or different atoms according to their chemical reaction. They found that if you order the mass of those elements or those atoms, and they found a very interesting patterns. And after a certain number of numbers, they call this one mass. Basically, they originally used the mass to classify the to order the atoms. And they found that as you increase this masses, which actually are discrete numbers. Okay, so that's probably the first discovery of quanta, right? So the mass are actually a lot of continuous variables. Okay, so they take discrete values, and they found that as you increase this mass step by step, the chemical properties actually will change, but they will come back. Okay, so they found this periodic behaviors of the atoms' chemical properties as a function of the mass. Okay, so they call this one periodic table. So, and how to understand this periodic table also is a very important, a task for the new scientists in the early 20th century. All right, so let's take a break and do a small quiz. This quiz is that which of the following technologies or concepts did not play a role in the formation of the modern concept of atoms? A, ideal gas law. That's the PV equals to nRT, right? B, ideometry. That's the technology to collect the gas and measure the pressure and temperature and volume, okay, in the chemical reactions. And C, optical microscopy, right? Using the high resolution of optical microscopy to see the atom, for example. And D, conservation of mass in chemical reaction. So let us do a poll. So you can just click on A, B, C, D, E as you think correct. There could be more than one choices. Okay, we're going to use 1 minute. Okay, so try to, if you haven't make your choice, you can bet. You have 3, 2, 1 seconds. Okay. Okay, so among the response, you can see. Let me share this result. Actually, most of us got the correct answer. That's C. Okay. And optical microscopy was already invented then, but it's not sufficient to. The resolution is not sufficient to see the atom. Okay. Instead, those smart chemists they use this macroscopical measurement and reasoning to deduct the existence of atoms. Okay, so that's a very smart idea. Actually, in physics, people very often use this kind of smart techniques and the logical thinking to deduct the conclusion before they actually see them. Okay, so we're going to see a lot of such kind of examples later on. All right, so we have done this story, and the next story is about the light. It's a wave. Okay, actually, more specifically, light is EM wave. Okay, and this was mostly done by Faraday, Maxwell, and Hertz. Of course, that also leads to the theory of relativity by Lorentz and Einstein due to experiment, partially due to the experiment by Michelson and Murray. Okay? right? And there's also Young's double is a double slit experiment, but that was actually done before the EM theory. Okay, so I used a double headed arrow to connect the two. Okay, and then this one we need to, of course, the observation of the atomic spectrum. So actually, mostly because of the Young's double slit experiment, not because of the EM wave theory of light. Right. So this experiment actually was really important. We know that in the history there were two theories about the nature of light. One is mostly with the most important promoters are Newton and Descartes, and they say that the light is made of particles. Basically, they call a corpuscular theory of light. And Huygens had an opposite theory. He said light must be a wave. Okay? And then a decisive experiment was done by Thomas Young in 1801. And he passed the light through a single slit first and make this one to a point source. And then passed the selected light through two slits. And then amazingly, he observed the interference pattern on the screen. Okay, so this is extremely important experiment in the history of physics. Okay, it established the wave nature of light. Okay, and of course later Maxwell, Faraday and Maxwell developed this Maxwell equations for the EM wave, and by calculating the speed of these EM waves, and you can find that they are close to the light speed known by the time. Okay, so it's conceivable that the light could be just EM waves. But then this, of course, was verified by Hertz, and Hertz used this sparkling setup, okay, and create. They can just use the EM sparklers to create light, okay, and they receive the at a point far away, okay. And also, interestingly, of course, in the same setup, in the same experiments, Hertz also discovered the photoelectric effect, which of course leads to the theory of light as particles. Okay, that's very ironically. Okay, and of course, Michaels and Morley, and then measure the light speed along different directions on the Earth. That disproved the existence of ether, which was postulated by Maxwell. And then Lorentz and Einstein developed this relativity theory, of course, along with a lot of other people. Okay, so this is the history about a very brief history of the light theory, right? And then eventually, so that is to this kind of famous formula of Einstein: m squared c squared that equals to e squared minus this momentum square times c to the power 2, right? Okay. And actually, when Thomas Young did this double slit experiment, he also invented this diffraction grating. And technically, this is technological wise, this actually is a very artful achievement. So Thomas Young created the gratings with 500 grooves per inch. So that means he could have got a very good resolution for the light. And then this device was immediately used to measure the spectrum of light. Okay, so that means you can separate the lights of different wavelengths into different directions, and then you can easily detect them. Okay, right, and then immediately William Wollaston in the same year, and he discovered there were 5 strong dark lines and 2 faint lines in the solar spectrum. Right, so once you can resolve the spectrum of the light from the sun, and then you can actually see this kind of dark lines, right, such as this one. Of course, later Fraunhofer measured this one more systematically and showed that actually a lot of dark lines in the solar spectrum. Okay, and then there are a lot of follow-ups, for example, by Herschel and Torbert, and they observed the the lines, the spectrum of salts in the frame, and they found that they have lines brighter. Okay, and then later Wisdom, okay, they can distinguish the lines of different metals. Okay, and Foucault made a very decisive finding, and that the absorption lines and the emission lines, they coincide. They're the same, right? So that you can have the light be emitted at this frequency, and then this material must emit the light at the same frequency or the same wavelength, right? And then Kirchhoff immediately got this idea that those spectral lines of the solar spectrum must be related to the absorption of the chemicals on the surface of the sun. And this, of course, become a very useful technique for the astronomical observation, right? So now you can see the elements actually in a star far away from the solar system, right? And also you can use this one, for example, to measure how fast the universe is expanding, because now you can easily compare the spectrum of hydrogen here and the spectrum of the hydrogen there, and see how much is red shifted, and then you know how much they are, receding from us. Okay, so that becomes very useful technique. But the most important thing is that there are discrete emission or absorption lines, and for the same matters, the emission lines and absorption lines, they coincide, right? And then Balmer, by studying the positions of these lines of elements, and found that for the hydrogen, there's a very beautiful formula. This is empirical, of course, but this formula is very beautiful. It's 1 over lambda equals to, a constant called the Rydberg constant, and that's times just 2 fraction numbers. That's 1 over 2 squared and minus 1 over m squared. M is greater than 2, of course. And then Rydberg actually found a more universal formula for all the sodium, potassium, magnesium, calcium, and zinc, and so on and so forth, right? For a lot of elements, okay, using just one single element, okay. And then this was later generalized by Rees, okay. There are different series, but they all have this kind of simple formula with a slight modification of those integer numbers in Balmer's formula. This, of course, is very interesting, but the question is why, right? So now let's take a break. Okay, of course, I should also mention that Seaman and put these emissions in the strong magnetic field, which actually is very difficult. He made a Laurent grating with a radius of 10 feet. 10 feet is 3 meters, right? So this is a huge grating with 14,939 lines per inch. So there are many lines of this one. So this one creates a magnetic field of 10 K Gauss, that is 1 Tesla. And he measured the broadening of the D lines of the sodium and also the splitting later on, okay? And he explained this one by the Lorentz force, okay? And later they found that this one actually is it's verified by the polarization measurement of the light emitted by these atoms in the magnetic field, okay? Right. And interestingly, using this theory, this Lorentz force theory, and you can estimate that this kind of charge to mass ratio, and found that this actually is more than 1,000 times that of the hydrogen ion. So this is a big surprise. It's kind of unknown, okay? You do this measurement, and then you find that if we suppose this one is, because there's some kind of a charged particle moving, and can explain this splitting of the D lines. But then this kind of particle must have the charge to mass ratio to be too large. That means the mass is too small as compared to the mass of the hydrogen. So this is a difficult and surprising, discovery. Okay, and then later, of course, and Lamo I also give another way to explain this one based on the circular orbits under the torque of a magnetic field, give the same results. But later on, there were further discoveries by Michelson and Preston that the spectral lines actually could split into 4, 6, or even more components, which actually are inconsistent with Zeeman or anomalous explanation. So they call this one anomalous Zeeman effects. So all of this one, requires explanation, okay, by the time of 1900. So let's take a break, and then we can come back to do the quiz, okay? So let's take a break of 15 minutes and come back at 10:40, okay? All right, so let me enter the polling. And so this requires a little bit explanation. So in some sense, all of these 4 choices make some sense, okay? But there are some loopholes, okay? So for A, the dark lines of the solar spectrum are due to absorption of atoms at the surface of the sun, which are more or less correct, but not exactly, because the sun, this solar spectrum also passes the atmosphere of the Earth. So the atmosphere of the Earth will also contribute to some lines in the spectrum, okay? So these are not exactly true, but yes, many of the dark lines of interest are due to the absorption atoms at the surface of the sun. And B actually is correct. Different elements do have different spectral lines, okay? Because they have different transition energies in the atoms, okay? There's no such coincidence that the 2 elements actually have the same spectral lines. So the spectral lines can be used as the fingerprints to distinguish element. This actually is an important method in the chemical analysis. And C, the brightness and the darkness of the same elements must match. Of course, this is correct. And hydrogen atoms in different galaxies have different spectral lines. You can say this is wrong because they must be the same, right? In nature, but nature they must be the same. But if you take this as the spectrum observed on the Earth, they are indeed different because of the redshift. Okay. And the spectrums of the elements in the faraway galaxies are all redshifted because they are receding from us. Okay. Because of the Doppler effects. So they are redder than what they have been emitted when we observe it. Okay. Okay, so this is the explanation of this quiz. Okay. Oh yes, sorry for the typo. Yes, thank you. Absorption of the photons, not the atoms. Yes, in this sense, this is wrong, right? Okay. So say the absorption by atoms. Okay. And there's also a question for you. So if the spectra of the atoms are all discrete lines, why do we have continuous spectra at all? So anyone has any hints? And question A, why the absorption of Earth's atmosphere is relatively unimportant? Not unimportant, actually they are important. But in the early days, some of this one first of all, they are mostly done by molecules, right? There are very few single elements at the atmosphere of the Earth, so they are rather complicated. Okay. So the answer, the interaction between atoms. Yes, some of this one, but actually, the spectrum of atoms are not discrete. They are continuums, first of all. Secondly, there are a lot of atoms, they are broadenings. And their interactions, as you said, are scattering. The scattering will broaden the discrete lines. Okay. And there are also, Doppler shifts. So there are many different ways of broadening. And the atoms do have this continuum spectrum above all of their discrete lines, okay, in frequency. So put all of these together, they are molecules that they also have discrete and continuum spectrums. When you have a system of many kinds of particles, molecules, atoms, actually we're going to have a continuous spectrum. Okay, and later on we'll come back to this one. That's called the black body radiation. Okay, so by this time, so we have learned, there's atomic spectrum, right? Because of the absorption of light of particular wavelengths. Of course, this is very interesting, but very mysterious at that time. So now I will come to another, pillar of physics in the early 20th century. That's statistical mechanics, especially the kinetic theory of gases. Okay, and this one will be later be applied to the light. Okay. So actually, Clausius and Maxwell have already applied this statistical theory to understand the viscosity of gases. Okay, and they find that there is a distribution of the particles in velocity, and they kept the energy partition for each degrees of freedom. And this is a famous formula that should be kBT, the temperature, times the Boltzmann constant divided by 2. Okay, right? According to this distribution of velocity. And then, of course, an important discovery is made by Clausius, Boltzmann, and Maxwell, not in the 1960s, so the 1860s, sorry about that. and the entropy, and is given by minus Boltzmann constant times the logarithm of the probability. Okay, and this probability of a state is given by the energy, by e to the power of minus energy over kBt. Okay, so these are the important discoveries, especially by Boltzmann in the 1860s. Okay, and Maxwell actually, devised this device to measure the viscosity, and this is a very smart device, worth a little bit, staring. So you can see that they use a pendula in a sealed gas, and this pendula has a magnet, so you can use the magnetic field to drag, use a magnet to drag this pendula away from the equilibrium position, and then when you release the magnet, this is going to start to oscillate, and then they use the light, so to do the refraction. So when these are different positions, you can see the light will be reflected at different point, right? And then you use this one to measure the fluctuations and this kind of and the vibrations of this pendulum, and that one gives us information about the viscosity of the gases. So it's a very smart design, okay? Right, and that of course verify the kinetic theory of gases. Okay, and Einstein, furthermore, in his PhD thesis, actually, he developed this molecular theory of Brownian motion, and found that the free path of a particle embedded in a liquid or in a gas actually has the relation given by this lambda squared average given by kBt, the temperature, times the time, okay, divided by this 3 pi VA. So this is the diffusion, okay, and they found that so the diffusion of a macroscopic particle is fundamentally related to the macroscopic properties of the system. But especially you can see that the K and the K, the Boltzmann constant showed up in this formula. Okay, so this actually is a very profound result. And the verification of this formula gives a definite proof of the molecular theory of liquid and gases. Okay. And then later, this was verified by experiments by Perrin. Okay, this is also a very smart experiment, and used the pollens, suspended in the liquids, and use the optical microscope to, to observe the path of those pollens in the liquid, and verify this formula by Einstein. And Perrin remarked that I think it is impossible that a mind free from all preconception can reflect upon the extreme diversity of the phenomena, which thus converge to the same result without the experience a strong impression. And I think it will henceforth be difficult to define by rational arguments a hostile attitude toward the molecular hypothesis. So that means this experiment, agreeing with Einstein theory, give a definite proof of this molecular theory of liquids and the gases. But this, of course, is a very important development in the atomic theory and the molecular theory. Okay. And then apply this one to light by Stefan Boltzmann, Ryan, Rayleigh, and Planck. That gives us a very important foundation of quantum theory. That's called a black body radiation. All right, so let me explain a little bit the early stage of this theory. And first of all, actually, the Maxwell considered this EM radiation, the electromagnetic radiation, as a gas. And found that the pressure of this gas on a conductor versus the energy density has the same formula as that for a molecular gas. That's interesting. The pressure equals to Epsilon over 3. So this is the same for an ideal gas made of atoms or made of molecules. Okay. But of course, Maxwell was using a kind of EM radiation and calculate the pressure on the conductor surface. And later, Stefan Boltzmann found a formula, and that related the radiation rate versus the temperature, which is given by d over dt, the emission rate. is proportional to the temperature to the force power. Okay. And this one actually, so we can skip these details. So this one is determined, totally by thermodynamics. Okay. So I give this detailed derivation right here, but you don't have to follow this. But I just want to give you an impression that using only thermodynamical relations, you can actually find out the emission rate of a radiation is always proportional to the force power of temperature. This actually is an important formula, and is a foundation, it's a stepstone for the later theory on the statistics of light. And William, give a very smart argument. He put suppose you have a box, okay, with electromagnetic waves confined within the box, and he did this kind of adiabatical argument, say that you do the adiabatical expansion, okay, and then you find that this temperature and the volume must be constant. The times of volume to the third power must be a constant. Okay, and this immediately tells us the temperature should be proportional to 1/4 lambda, the difference. And then you use the Stefan-Boltzmann's formula, just by simple dimension analysis, you can find the energy density, that is the total energy of the light per unit volume, within the wavelengths from lambda to lambda plus d lambda should be u lambda times d lambda equals to minus fifth power of the lambda times d lambda, and then times a function as a dimension, as a product, a function of the product of lambda and t, okay? Right, so this tells us you must have some formula like this one, right? But if you translate this into frequency, the energy density in terms of frequency, that should be the frequency to the third power times a function of V over the temperature, okay? And then, of course, this was measured using the apparatus. You can hit a cavity with a small opening, and then use the spectrometer, right? The spectrometer, invented by Thomas Young, and you can measure the spectrum of this emission and the intensity as well. And they found that actually the Stefan-Boltzmann law is indeed satisfied, okay? But there are some caveats later on. And then according to Williams' formula of energy density of black body radiation, right? You should write this one in terms of frequency like this one that I said before. So this is the question for you, okay? So if this function is written as a dimensionless function times a constant, suppose you have a function like this one. So as a physicist, an immediate, impulsion is to write down this one as a dimensionless function, right? You have V over T, and you don't have any other physical quantity to show up in this formula. So you must add some constant to make this one to be a dimensionless number. But we know that there is light velocity. There is a Boltzmann constant Kb. But no matter how you massage this formula, you find that there's always something missing. Okay, you could never make this frequency over the temperature times the Boltzmann constant, times light velocity, to whatever power, make this into dimensionless. So that means you must miss some constant, right? So this is actually as a physicist, this usually is that there is an important piece of physics missing, in this process, because you are kind of lack of physical constants to make this formula to be dimensionless. Okay, so that is something, is an important hint. And another feature of this one is that you can measure, you can see that you can always find that this is the homework problem. Okay, you can always find that the maximal of this energy distribution, at a certain frequency, a certain wavelength or certain frequency, call this one lambda max. this lambda max times the temperature should always be a constant, no matter how you change the temperature. Okay, so you're gonna have the spectral shift, but this one must be a constant for the same reason, right? Because you have a function of lambda times t. Okay, so when you maximize this one, you can always find this one to be a constant. Okay, right? But then again, you know, if you want to make this one into a dimensionless quantity, you are missing that constant, right? So that's another hint of the, you know, missing part in this physics. Also, you can ask if I want to do the time expansion of this f, what would be the leading term? Let me ask. So will the leading term be a constant, or be just a power of nu over t? Anyone has a hint? So the answer is the time expansion of this function f should not be the leading term should not be a power of nu over t, because if that's the case, this nu can be always absorbed into the prefect nu to the third power, right? And then that will make this nu to the third power to nu to the fourth power, for example, or to the fifth power, for example. And that will violate the Stefan-Boltzmann law, which is determined by thermodynamics and cannot be wrong. Right. So that means the leading term of this f must be a constant. But if you write this one into dimensionless, so f must equal to 1 plus something, right? So this is another important hint, okay, for small nu, okay? If nu is small, you must have this one to be something like that. And for the experimental measurement, they use this kind of black body measurement. So the technique that you have a cavity, a large cavity, and make a small opening, and then the emission from this one should be black body. So that means this is universal. It does not depend on the properties of the materials that are used to make this cavity. Right? It has a lot of surfaces inside. It can be made of plastic, it can be made of metal or whatever. But as long as this hole is small as compared with the whole body, and this emission should have a universal spectrum. That means it only depends on the temperature. Okay, that's the only thing that you can change, not dependent on anything else. Do you know why? Why do we need a small opening to do this? Okay, so I will not give you the answer, but I'll give you the hint. The hint is that at the thermal equilibrium, the emission and the absorption should be balanced. And suppose you have a small hole, small opening in a big room, for example. So if you try to peek inside, what would be the color of this opening? Okay, right. So that's the hint. And so they use this kind of device, as showed in the previous slide, the spectrum of the black body radiation. Of course, they found that the lambda maximal times this temperature and always goes like this way, okay? And it rises up when you have this, the wavelength increase, and then eventually decrease when the wavelength goes to very long, okay? And this one, this kind of universal spectrum has been used for a lot of applications nowadays. For example, in the remote sensing, in measuring the temperature of a star, in measuring the speed of a galaxy, okay, in measuring the cosmic background radiation, and so on and so forth. Okay, so it's actually a very useful technique nowadays. Okay, and then to fit this spectrum, and Ryan actually made a conjecture. He knows that his law should be something like nu to the power 3 times the function of that one, right? And we also know that this function f should expand as 1 plus something, right? So very natural, guess should be e to the power minus nu over t, and there should be some constant. And this constant should make this e power, this index in the e power to be a dimensionless number, right? So we know that there's KBT, that's fine, but there's something missing, right? So you should put a beta over there. Okay, of course, we are use beta, and later on we know that this one should be h, okay, the Planck constant. But never mind. So we just like this one to be h, okay? But anyway, just a notation change. But if you put this one together with experimental data, you find that indeed, for the high frequency, this is a quite good formula. But if you compare this with the low frequency, it's not really correct. Okay, you find something wrong. Okay, right. So this is not a. So Williams formula does not agree with this this one for the low frequency end. Okay, and actually you see that. So this one is the experiment data shows something like nu to the power 2, and Williams formula is nu to the power 3 for low frequency. And Rayleigh and James actually they use another way to derive the radiation spectrum. Okay, they find that the density should be just the square of the frequency. Okay, so the idea actually is it's very simple. You consider a box, and then you have standing waves of light within this box. If this is a black body, so the light cannot go out, so there must be standing waves inside. And they can count the number of moles, the number of possible standing waves in the volume for a certain frequency. And that one will give you this, okay? So this will be done in the access class. And I will also give a note on this. So basically, it should be v squared times nu squared times d nu. That's the number of moles, okay? And then according to the Boltzmann distribution for energy, and so the energy per mole can be easily calculated to be just kB times T. Okay, so you put this together, you got this Rayleigh-James formula. Indeed, you find that this formula agrees with the experimental data very well for the small frequency, but for large frequency, you have a problem. So the problem is that it diverges. Okay, not only disagree with the experimental data, but also diverge. So that means we have this so-called ultraviolet catastrophe. This was named by Paul Ehrenfurst. Okay, we have divergence at the high frequency. So this gives a critical question to the community. That's another cloud according to Kelvin. Okay, and Planck was to the rescue. Right, and Planck found that Weyer's formula is good for the high frequency, like this one, right? And then you know that this function fx for the high frequency should goes to 1 over exponential of x. For the low frequency, it's 1 over x. And for low frequency, that means for small x, you know that this exponential should expand as 1 plus x, right? So the easy way is that if you minus 1 over here, you can go to 1 over x. So a natural guess is that this fx should be 1 over exponential x minus 1, right? So that's a very natural guess. And if you put this together, indeed, you find that this formula is exactly, the same as the experimental data. Okay, so this is Planck's law. And then the question is how to understand this distribution. Okay, right? You have 8 pi nu square over c cubic times the constant times nu over this exponential function minus 1. Okay, so that's the Planck's formula. And this one, of course, you can see that at the high frequency limit, just approach to Weyer's formula, and the low frequency limit just approach to the Rayleigh-James formula. Great. And also, you can calculate this from this maximal wavelength, lambda max times t equals to about 2.9 and to times 10 to power 3, minus 3. meter Kelvin, and the Boltzmann constant, you can actually find out this constant H should be about 6 times 626 times 10 to the power minus 34 standard international unit. Okay. And to explain this one, and actually Planck tried to work out the, this energy dependence, the temperature dependence using the entropy from thermodynamics. They found that if you have, to fit this temperature dependence, and here we got the entropy of this oscillator that radius, this wave, it has formed like this one. Okay, you don't need to know the details, but it's something like this. And then he tried to, if we assume that the energy of this harmonic oscillators, I divide it into R portions. Each one has a portion energy of epsilon, and then you separate this one into n oscillators. Okay, and then you know that there are different ways to distribute this energy, right? So they give you the number of ways, the possible number of states is given by this W, and use Boltzmann's formula for the entropy, you can go this way. And if you compare these two, immediately find that you just need to put this epsilon equal to that constant B. Right, you can go the same entropy as needed to fit his formula for the distribution. Okay. And of course, this is like a miracle. So how could Planck, come up with the idea that the energy, should be a discrete portion, right? And Planck didn't say how he got this, but many people guess Planck probably worked backward. He probably using that entropy, and then do the transformation, and to find out what is W, and from that W, he found that there must be a discrete portion of this energy. But anyway, so this gives us the most important, the first breakthrough in quantum physics. That's the introduction of energy, quanta. Okay, so epsilon equals to Planck constant times the frequency of the oscillator. So this is a crucial result. So oscillators emit quantized energy, and this result actually is so crucial that even Planck did not appreciate, did not accept it until 1908. And he had to try to, devise a lot of classical mechanical mechanisms to try to explain this one. Of course, that was in vain, right? But he didn't regret. He said that my futile attempts to fit the elementary quantum of action somehow into the classical theory continued for a number of years, and they cost me a great deal of effort. Many of my colleagues saw in this something bordering on tragedy, but I feel different about it. Okay. All right, so now we can kind of, with the hindsight, understand Planck's formula to soften the UV catastrophe. We know that in the Rayleigh-James formula, the important is the average energy of each mode, each standing wave mode. That is given by the Boltzmann distribution. So it's energy equals to KB times T. But Planck is energy equals to epsilon over exponential function minus 1. So you can see that when this temperature goes to, when the temperature goes to very, very small, so or when this epsilon frequency goes to very small, very large, the Rayleigh-James energy portion actually is still constant. So it's independent of the frequency. But for Planck, it will vanish when the energy quanta is high or when the frequency is high. Okay, so this gives a solution of the divergence at high frequency. So actually, this is a very nice analog made by Green, okay, in his book of The Elegant Universe. So you can compare, suppose there are two companies. One is called Rayleigh-James Company Limited, Corporation Limited. I suppose in this company, you are paid $100 for completing a job. But you can also complete the job partially, and then you got paid by, X dollars for X% of the job completed. But in Planck's company, you are paid $100 for completing the job. But if you only do, say, 17% or even 83% of the job, you got no pay at all. Okay, so you have to complete the job and got the pay. Or you don't get anything, no matter how much, fraction you have completed. And now in the second company, Planck's company, actually, the company will not be bankrupted, even the probability for, even the number of people try to working for these high payment jobs increase in polynomials with the payment. Because the probability for completing a high payment job, of course, which are difficult, decays exponentially. So you can put this together, you can calculate the average payment by Planck's company will actually go to zero if there are such kind of high payment jobs. But in Rayleigh James company, this one will soon diverge, and then the company will be bankrupted. So that's why the Rayleigh James formula is bankrupted at the high frequency end. But the Planck's formula well behaved. Okay, right, so this is kind of a Planck constant, right? So that's H equals to this constant. And actually Planck used this constant and he, under the experimental value of KB and this ideal gas constant R, he obtained the best values at that time, the Avogadro constant and the electron charge, which are quite close to the experimental value later obtained, okay? And also we know that in physics, Planck's constant are important along with the gravitational constant G and the light speed, okay? That can be used to define the natural scales for time and for length and for mass. Okay, these are called the Planck system of natural units. Okay. And now I should mention the importance of this dimension of Planck constant. So if you look at this Planck constant, of course, Planck constant H times the frequency nu equals the energy, and nu has a dimension of 1 over time, right? So that means the dimension of this Planck constant is the energy times time. And this one can be also translated as the momentum times the distance. And it can be also translated into the angular frequency times the angle. So with the hindsight, actually, this is the dimension analysis of this Planck constant is already very, very suggestive. Okay. For this reason, actually, Planck actually called this constant as the quanta of action, because it has the same dimension of the action. Okay. So Planck remarked it. So the thermodynamics of radiation will therefore not be brought onto an entirely satisfactory state until the full and the universal significance of the constant H is understood. So this H actually plays a fundamental role in the quantum mechanics. Okay. And last year, and the new unit standard unit system, the international standard unit system has been defined, and using only some fundamental properties of particles and the constants. And the constants include the Boltzmann constant, the light velocity, and the Planck constant, Avogadro constants. Okay, and then the other things are the electron charge and the frequency of a Celsius transition in a Celsius atom. Okay, so putting all of this one actually can define all these kind of units of the mass and length, time, current, temperature. There's another one that's for the luminosity, which we're not concerned at this point. Okay, so after this work, actually Planck didn't write any papers on the subject of quantization for 5 years until 1906. And in 1906, Planck described the two versions for understanding this kind of radiation of quantized energy by oscillators. So one is that the energies of these oscillators must take the values of 0, epsilon, 2 epsilon, 3 epsilon, and so on. That's one possibility. Another possibility, because of some mysterious mechanism in classical mechanics again. And the second theory is that the molecules can be considered as to lie within the energy ranges 0 to epsilon, and then epsilon to 2 epsilon, and 2 epsilon to 3 epsilon, and so on. So that means those molecules will arrange themselves so that their energies only feel comfortable within these energies ranges, okay? Because of the interactions between them, for example, okay? They form these energy bands, okay? And actually, Planck's theory did not, in any sense, gain immediate acceptance. Okay, there were no further papers by Planck himself or others until Einstein's papers of 1905 and 1906. That actually make a big leap forward in the development of quantum theory. All right, I think this is very much what we needed to complete today's lectures. Before we leave, let's do a simple quiz. That is, if the temperature increases, the absorption spectrum of a black body would A, have the peak blue shifted, B, have the peak red shifted, C, have the peak position unchanged, or D, none of above. So let's do the quiz.